In this video, we're going to build the Anaqsim model that we've used as part of one of our case studies on our website. So the case study, which I'm showing here, is looking at some deep well dewatering. So we've got 4 deep wells and an excavation basement. In the case study, we then sort of compare the Anaqsim results against some mod flow results and also against some sort of empirical equivalent well method equations that are presented on the website. So we'll get straight into the model build. So if we first open up Anaqsim, and step 1 is always to save your model file. So if we will go to model, we'll save it. The next thing to do is if you've got a background map, it's good to load that. So if we go to plot input, what to plot, you can select a base map. We've got a DXF there. We'll just go and save again. And hopefully if we do make plot, there we go. If we zoom out a little bit, we have, similar to what you saw on the website, 4 dots where we're going to put our wells, and then this is the excavation basement. Step number 2 is always to define your domains. In this, we're going to have a single domain. So we'll go to model input, domains, confined or unconfined. And I'm going to type in some details here. We'll just call it aquifer because we're only going to have one. It's unconfined. All of the sort of details of the aquifer you can find on the website. So this is 100. Our bottom elevation is 70. Average head. This is what the level of the groundwater is going to be at the start of the model. These ones are staying as default. And then the K value is from the case study details. Putting this K1 star 0.1 is just a way of making your K3 values dependent on what you put into K1. So we'll save that. Go back to the plot window. There's nothing to plot yet because we haven't actually put in any boundaries, but the next step 3 is going to be putting in our boundaries. So we start with the outer boundary. Because we don't know a lot of information about the wider sort of site, we're just going to go for one sort of very large round external boundary, which is very simple to do in Anaqsim. You can go to model input, line boundaries, head specified external with gradient. So we go to drop down here, aquifer. Then it's a big circle, so you want to know where the origin is. So that for us is going to be at 1,000. We want to make the circle 1,000 long, and we actually want a gradient across it of our head levels. So it's a very shallow gradient, and we're going to give it a direction. We go file, save, and we will make the plot. If I zoom out here, there we go. We've now got our external boundary, which is just made up of, I think, 12 segments going round. We could solve the model now and see what that looks like. That's always helpful to do at this point to make sure you've got your external boundaries in the correct place. So I'm just going to go solve. And then we can, if we change the plot input and we turn on contours, that helps us to see what's going on. We'll do make plot. I'll zoom out here a bit. There we go. We have some contours, so it's just a sort of steady gradient across the site at the 49 degrees that we specified. I'm going to set the plot to the current view, and then that means it will always plot this view going forwards. So next we want to add some internal boundaries. In this model, we're only going to have those 4 wells that are located at these points here. So we will go to model input, pumping wells, and we're going to specify the head. We're specifying the head because we know how much we need to draw down the groundwater so that we can start excavating. So we've got one in the northwest corner. It's going to be in aquifer domain, and then it's XY coordinates. You can just type these in, or you could sort of sample what those coordinates are from the plot window. We do the radius as 0.2, and we are going to specify a head of 84.5. That is what water level we want to draw down to. And then enter will get us a new line. Go northeast, aquifer. Now, if you don't want to type these all in, what you can do as well is go copy the selected row and paste new rows. So I'm going to do that twice, and then I'm just going to change the name. And we're going to change the coordinates. Right, file, save. If we make the plot of just going back to the model elements only, it will get rid of the solved model, but that's fine. It's very quick to run. And you can see we've now got green crosses where those wells are located. Now, we actually want this model to be a transient model, and in transient models in Anaqsim, you have to add what's called sort of recharge nodes. So that's our next step, step number 4. And for those, you have to go to model input, the area source sync, and we're going to set a fairly coarse resolution of these nodes across the whole domain, first of all. So we'll go to that one. We want it on the aquifer. This, you can here specify sort of a recharge if you wish to apply a recharge to the model. We're not doing that on this one. So, but what we do want to do is a node spacing of about 200. I'll save. Now, if we do the make plot, nothing's going to come up from that change because we need to change what we're plotting in what to plot here. So instead of elements, we just want with details and control points. And now we will make the plot again. And we've got these little plus signs, green signs. So that's where we've got our, what we're calling recharge nodes. Now, you want a higher density of recharge nodes where you're going to have a lot of vertical flow. So in this case, that's going to be around where our wells are. Now we've got a special type of recharge node that you can apply in Anaqsim, which is linked to each well. So as you move the well somewhere, those extra nodes are going to move as well. So we're going to put those in under area source sync, and they're called well basis points. So it's always better actually to write something in here first before you select what wells you want. So we're going to go for 10. These effects for the spacing is, which will make more sense once we look at it. And we're going to select all of our wells. There we go. I will save, and we'll make the plot. Now, if we zoom in closer, we have now got more of these green pluses. I'm just going to set the plot to the current view, and then we're going to replot again. There we go. Now you can see them. There's a much sort of clearer picture. If I zoom in again on one of them, you'll see that the density of those is increasing as you get to the well. And so we're getting to get better resolution for our vertical flow in the vicinity of the well. Next, because it's a transient model, we want to set up some time steps. Before we set them up, we just need to go to General, and at the moment it's set as a steady state. So we're going to untick that, which will make it a transient model. You can write in here length units and time units. It doesn't actually change anything in the model. You need to be sort of consistent in what values of sort of discharge you're applying. This is just helpful for other users of your model to know what units you are using. Back to model input, and we'll go to time steps. We just want a single time period, but it's going to be a length of 70 days. We want to split that into 10 steps, and we'll put a step multiplier of 1.1. This means that those steps will be fairly uniform throughout the 70 days. If it was a value of 1, then they would be completely uniform. The higher this value is, the more sort of bunched up those steps are towards the beginning of your time period, which is useful if you've got rapidly changing pumping rates. One more thing we need to change for the transient model is we need to go to Model Input, Solution, Solve Settings. And the transient models need a starting head source, so you need to be able to tell them what the groundwater level is before you start. Now, you can either do that by providing it a file with outputs from a previous model run, or you can put it as constant. We're going to go for constant, and then it's going to take the value from, if we go to domains, it's going to take this average head value and use that. Before we solve the model, we're going to actually assign some sort of analysis points. So this is where you'd like to extract out information, or it might be where there was a monitoring well. So if we go, instead of to model input, if we go to analysis input, we are going to add in some hydrograph points. So we want to assess what the sort of drawdown effect is in the center of the excavation so that we can work out whether it's ready or not for excavation. So we're going to put one at center, and that's going to be right in the middle of the model. And we then also have got a few more that sort of correspond with where information was taken from the case study. These are all heading northwards from the centre. Right, we will save that. And if we plot it, they're not going to show up immediately unless we change under what to plot. We want to add in analysis inputs. Okay. So now if we go to solve, it's gone through all of the time steps. So we will now go to make plot, and we're going to choose a level time. So we've got all of the different time steps down here. If we go to one near the beginning, you can see we're starting to get some drawdown around the wells. I might zoom out a little bit. Plot input, set the plot to the current view. Make plot, same level time. If we then plot at a later time, we've now got a much wider drawdown, whereas before it was much more localized. So if we now want to extract out information about what the head levels are in various locations, those 4 hydrograph points we previously put in, just I'll zoom you in here. These little circles here are the hydrograph points. We can go to Analyze, Head Hydrographs, and we can graph them. You can add your own observed values if you wish to at this point. And here we've got a graph of the drawdown over time of those 4 observation locations, with the one in the centre being the one seeing the largest drawdown. Another thing we're probably interested in is the pumping rate, the discharge rate from the wells. So we can go to Analysis. There are a head specified well, and you can either graph the transient discharge, or you can write the discharge to the run log or to a CSV. If we just graph it at the moment, we're going to we'll just select one of them because I think they're all very similar. And you can see that this discharge is negative. So whilst we've got a very high discharge rate right at the beginning, that gradually decreases over time.